today we are going to see the definition of semigroup of operators, linear operators, okay, and given a C0 semigroup, that means semigroup of linear operators which has some continuity property, we would define what do we mean by generator of the semigroup. Okay, so here before talking about this, we must understand that a semigroup of operators is essentially a collection of operators, correct? And that collection is parameterized by a parameter we call that's a t. So you can think t is like a time parameter. And there in that collection of operators, the members of the collections are related in the sense that they have an algebraic structure, that is semigroup structure they have. Okay, so that means that collection has one identity operator, of course, I operator, and with composition. Okay, composition operations, okay, they form a semigroup. That means that given two operators, their composition operator also lies in that same collection. Okay, and that composition operator is here associative. Okay, so here we start the definition here. So a C0 semigroup of operators t greater or equals to 0. Okay, so these operators are which are defined on a Banach space V is a map T from R plus, that is closed 0 to open infinity, to BLV, that is set of all bounded linear operator on the Banach space V. Okay, so here that small t is coming from R plus, and capital T of small t is an operator which belongs here. That means capital T of t is a bounded linear operator on V. So that means capital T of t takes a member from V to V, and it is a linear operator, and this operator also is continuous. Okay, so what we say in the language of functional analysis that we call the bounded linear operator. Okay, fine. Basically, it takes the bounded set to bounded set. Okay, so these operators, so we have a collection of such operators satisfying three conditions. One is that T0 of f is equal to f, okay, for all f in V. So V is the Banach space, f is a member of that. Okay, why am I writing f? Because actually the kind of Banach space what we would consider space of some functions, correct? So f would be some kind of functions on some set. Okay, so that is the reason to actually resemble with those notations. I am keeping this notation f. Okay, okay, then this semigroup property that capital T of small t plus s is nothing but capital T of t and composition with capital T of s, okay, for any t is non-negative. And the third property here, that continuity property. Okay, so that is saying that from the saying the right continuity, that Tt of f minus f. Okay, this is a vector now in V, but you take the norm, so you get a positive real number, and as t small t goes to 0, that should go to 0. Okay, anyway, we know that this f can be written as T0 of f. Okay, so you are saying that Tt of f minus T0 of f, okay, is going to 0 as small t goes to 0. So this is basically continuity property of capital T, okay, at time 0 from the right side. So if this happens for all f in V, we call this C0 semigroup. Okay, fine. So this is this type of continuity is that for every f we ask this, correct. So this like pointwise continuity, correct. However, one can define some stronger notion also, so we would come to that later. So let TT, this collection of operators, what we call as semigroup, satisfying these properties. So let TT be a C0 semigroup of operators. The domain of the infinitesimal generator of the C0 of the semigroup is defined in the following way. So here, when I say generator, okay, so that would be also an operator. Okay, so that would be an operator, but what should be the domain of the operator? Okay, so that is also one interesting question one should ask. Okay, so necessarily it is not necessary that the domain of the operator which is generator, okay, is not important necessary that the way we are going to define the generator, its domain would also include the whole space V. It is not necessary. So here we actually define both together, the operator and its domain. Okay, the domain of the infinitesimal generator of the semigroup is defined as so here first is the domain. We are defining the set of all possible f in V such that this limit exists. This is basically right derivative at 0, correct. Tt of f minus t0 of f divided by t limit t tends to 0. So basically it is right derivative of this, okay, if this exists, okay. So it may not exist for all f in V, then we do not consider those f to be in the domain of operator generator. Okay, we are not going to define the operation of the generator of for those f, but for only those f where for this exists, those we would retain, and this collection we call as D of A, or we say it is a domain of A, and then the formula of A is given below, that AF is defined as limit t tends to 0 TTF minus f divided by t. Okay. So this is the definition. So now one can ask that, okay, why should this be well defined for f in dA? Because that is the definition, that is the way we have defined the domain of A. We have defined domain of f so that this limit exists. So we have no problem. So when this limit exists, those f's are here, and whatever f's are here, for that when we compute this limit, what we get would be, we would say that, okay, AF. Okay, so A is the operator. Okay, if it acts on f, that would give me a right derivative at 0, correct. So right derivative of TTF at t is equal to 0. Okay, so that is the definition of generator of a C0 semigroup. Okay, we would see some examples how to compute this. Okay, then it would be a little clear. Okay, so here, so let us first consider the case where we have a dynamics, say for example a Markov chain on finite state space. From that Markov chain, we would articulate a particular semigroup, and for that particular semigroup, okay, after we define the semigroup, we would it would be actually trivial to check that, okay, that is indeed a semigroup. Okay, because it is very simple, and then after that we would compute what should be the generator of that semigroup. Okay, so let us do that now. So we take CT stands for continuous time, homogeneous finite state. So homogeneous means time homogeneous, does not the law does not change over time. Okay, so CT homogeneous finite state Markov chain xt on a finite state space on 1, 2, 3 up to n. Now we consider, since it is only finite state Markov chain, so we consider the transition times. Okay, so the transition probabilities. So at time t, if it is at I, given this information, the probability that xt plus h is equal to j, when h is a small positive number, so that probability can be written as lambda ij h plus small o of h, okay, when j is not equals to I. Okay, so this is the description of a continuous time Markov chain given a rate matrix lambda. Okay, so assume that you have that rate matrix. Okay, so assume that the rate matrix is already given, and that rate matrix is lambda matrix, which has n square entries, correct? N cross n square matrix. And the rate matrix, we recall quickly that that is a square matrix which is row sum 0, and off diagonal elements are all non-negative. So that means its all elements apart from diagonals must be 0 or positive, and the row sum should be 0. That means only negative entry should appear on diagonals. And this is a square matrix. So any such matrix is eligible to be treated as a rate matrix. Imagine that rate matrix is, and then rate matrix is actually considered as parameter for the Markov chain. Whenever we talk about some random variable, we talk about what is the parameter, correct? So our stochastic process, we talk about what is the defining parameters, coefficients. So here for Markov chain, this rate matrix is the parameter. So given a rate matrix, okay, there is only one single law of Markov chain. So the law of a Markov chain is determined from the rate matrix uniquely. Okay, so that is the description. You assume that we have that Markov chain. Okay, so we have this lambda, so we have this thing for all j not equals to I. So this left hand side we rewrite in terms of expectation. So probability of a random variable x belongs to A is same as expectation of indicator function of A at x. So that thing we are using now here. Probability that this is equal to j is same as expectation of this function xt plus h. If it is in j, then it is 1, otherwise 0. So we are going to get this left hand side. So left hand side is rewritten as expectation of indicator 1j of xt plus h given xt is equal to I. Right hand side is as it is, but this lambda ij we are rewriting in a little different way, that lambda matrix. Okay, so this is the rate matrix capital lambda, and then 1j. What is 1j? 1j is unit vector, okay, column vector whose jth element is 1, all are zeros. Okay, the standard normal basis, correct? The jth element of the standard normal basis. So that would give me jth column. So jth column is, and then the ith row of that. So ith element of the jth column. Okay, so that is nothing but lambda ij, right? So this lambda ij is rewritten in this fashion. Okay, so this is whatever I have written earlier. I am just rewriting in this fashion. That really helps for computing the generator of the semigroup, but the semigroup I have not defined yet. So I would soon define. Okay, and then small o of h here. Okay, what does it mean? That okay, so if I take divide both sides by small h, okay, and then take limit h tends to 0, so then this divided by h and limit h tends to 0 would go to lambda ij. Okay, so that thing only rewritten in this fashion with using small o notation. So again, now here for both these lines I have taken j is not equals to I. What happens when j is equal to I? So when j is equal to I know that from the law of probability that from the rule that sum of all events is 1. So this is the only thing which was kept aside. So the probability xt plus h is equal to I given xt is equal to I is 1 minus of this quantity. So 1 minus this lambda ij summation j not equals to I, all of this quantity. Okay. So this is pretty much clear what is expected. So this should be this thing. Now again this line I am rewriting in terms of expectation, okay, in terms of conditional expectation. So that I write down exactly this way, that expectation of indicator function, okay, at the ith set of xt plus h given xt is equal to I. So this is written as this one. And then this right hand side thing, this one I am rewriting as indicator function I at I. So of course it is 1, okay, it is always 1, okay. So whatever I you choose, okay, so this 1 subscript this I stands for the column vector which has only 1 at ith position. Basically this is the ith element of the unit basis, and then the ith element of that vector is 1 actually, okay. So this 1 is rewritten this way, and then minus lambda ij, okay, can be rewritten as lambda ii, because ith element of lambda vector matrix is nothing but minus of summation of all other elements in that same row. Why is it so? Because capital lambda is the red matrix which has row sum 0. So its diagonal elements are actually negative of the sum of all of diagonal elements in the same row. So that I am rewriting this way. So this is nothing but rewriting of this, okay. So I have one this thing here, another this thing here. So I call this B, okay. So I have A and B, the two equations here, what we have obtained just from directly this description, okay. So from A and B, now we get that for all I and all j in 1 to n, okay. So expectation 1j, so see that here in A I have expectation of 1j xt plus h, here I have expectation 1I xt plus h here, and here if you see carefully I have only one term on the left hand side, here I have two terms on the left hand side, but here in this term instead of I, if I put j where j is not equal to I, this term would become 0, so as if this is also there, but we have 1I of j, okay. So I can actually see that both are actually same equations. This is evaluated j when j is not equal to I, here it is evaluated I, because lambda ii is also can be written as lambda 1 ii, okay. So this way, so I combine these two things to write down expectation of 1j xt plus h given xt is equal to I minus 1j I is equal to h times capital lambda 1j I, okay, plus small o of h. So this factor, you know, if I divide by h and limit h tends to 0, that would be 0 basically, okay. So now we divide small h from both sides. So here I get expectation of 1j xt plus h given xt is equal to I minus 1j I divided 1 over h, but this here I have small h here, so h by h would be just 1 here, so I would be left with lambda 1j I, okay, this thing. Now this calculation we retain, okay, and then we define the semigroup operator. Although there in the description we have denoted semigroup operator as capital T of t, but here for some reason I have written S, capital S, okay, but it is the same thing. So assume that we have a family of operators SH, which is defined as SH acting on V, because V is the vector. So what is the Banach space here? The Banach space is set of all vectors on the set 1 to up to n. So n tuples, set of all n tuples. Or you can also view that set of all functions on the set 1 to up to n. Okay. Okay, so that is the space, and what is the norm we are going to take? We are going to take actually any say Euclidean norms. Okay, so because all norms are equivalent, it does not matter what norm we choose. So for now we choose Euclidean norm there, and then SHV is defined as expectation of V of t plus h given xt is equal to I. Okay, since it is homogeneous Markov chain, doesn't matter what my t is, it could be 0 or any other t, I would get the same value on the right hand side. So left hand side does not depend on t, so it is SHVI. Okay, this is defined by this. Is it a semigroup? That you can take as an exercise, easy exercise, that to see that this is indeed a semigroup. Okay, just by doing tower property and conditioning, you can see that okay, it has satisfied all three properties. That S0 V is equal to V. I mean that is actually just immediate, but when you put h is equal to 0, that means expectation of V of xt given xt is equal to I. That is nothing but V of I. Okay, so S0 of V of I is V of I. So that S0 is equal to identity, and then constructing S of say S subscript H1 plus H2 of Vi, you need to show that okay, that is S H1 composition S H2 of Vi. Okay, that you can do with conditioning, correct, using tower property. So this is a semigroup of operators, and it is also C0 semigroup. Why? Because as h tends to 0, this part, as the expressions what we have obtained earlier, from here we see that as h tends to 0, this part goes to 0 here. Okay, so and then for all unit vectors, right, so this instead of v I have this thing written for all unit vectors, but any vector can be written as finite sum of the unit vectors, the basis, and from there one can get that establish that it is also C0 semigroup. Okay, so this is the semigroup here, and for this semigroup now we are planning to find out the generator as we have defined in the last slide. So the definition of the generator was that you just take SH minus identity matrix and divided by H, okay, and operate on a particular function V, and that would give you the generator. But instead of operating on any particular arbitrary function V, we are calculating it on the basis vectors, okay, in that Banach space. So what are the basis vectors? They are all unit basis we are taking, correct? 1j. So this operating 1j, and after operating this, whatever the vector we are going to get, evaluate that vector at point I. Okay, this I. Okay, so this thing we want to find, but that we have already found here. We have already found here, correct? We have found that this SH is nothing but this thing, and this is identity operator on this thing, and we have already obtained that is lambda 1ji. We have already obtained that. Okay, so from the definition that this thing is A operator, so A operator acting on 1j at I is same as this lambda matrix operating on the 1j vector and divided at I. So that is true for all I and all possible j vectors. So what does it mean? That these two operators are coinciding on the basis vectors, and both are linear operators. So what is the conclusion? The conclusion is that this A, the generator, is nothing but lambda. So this is the proof that the rate matrix of finite state Markov chain is essentially the generator of the semigroup generated by that Markov chain. What is the semigroup? The semigroup is generated by this. Okay. Okay. So here we write down this conclusion that A and lambda both are linear operators are coincident. Yes, so this is the comment. Okay, so now we get back. So this, after looking at this example, we get back to again the further properties, etc. So this is a stronger notion of continuity, as I was talking that. Okay, we would come back to this. A semigroup TT, okay, of bounded linear operators on Banach space X is called uniformly continuous if following holds. What is this? That the operator TT minus the operator identity operator, so then the operator norm. So this is the subordinate norm, correct? So as we know that, okay, for when I have a linear operator on a Banach space X, then from the norm of the Banach space I can induce one norm in the BLX, the set of all bounded linear operators, that is supremum over norm of AV, okay. So where V is running on the unit sphere in that Banach space, okay. So that is going to give me the norm of the BLX, okay. So in that norm, if we take limit t tends to 0, if that goes to 0, then we say that this is uniformly continuous semigroup, okay. A linear operator A is the infinitesimal generator of a uniformly continuous semigroup if and only if A is a bounded linear operator. Okay. So this is an important, very important result. So when I start talking about, say, semigroup of operators, always semigroup of bounded linear operators, okay, that TT. But that does not necessarily imply that the generator operator, what we are going to derive, that would also be a bounded linear operator. That would be a linear operator, that is okay. But that would also be a bounded linear operator need not be true. Okay, the generator what we are going to get need not be a continuous operator. So here this theorem is saying that a linear operator A is infinitesimal generator of a uniformly continuous semigroup, okay, if and only if A is bounded linear operator. So that means for if we have a semigroup C0 semigroup which is not uniformly continuous, okay, then the generator what we are going to get would not be a bounded linear operator, would not be bounded linear, okay. So we know there's some examples of linear operator which is not bounded linear operator, correct? I mean, say differential operators are like that, okay. However, the example what we have computed recently, so there the generator was just a matrix. A matrix is of course a bounded linear operator, okay. So this result would then imply that, okay, that semigroup what we have obtained there is actually not only Caesar semigroup, that is uniformly continuous semigroup. Okay. Okay. So we are going to prove this theorem actually. So for a proof, what we are going to do, we are going to say assume A is a bounded linear operator. Okay. So and then from there we are going to show that the semigroup TT. Okay. So we are going to do that. Okay. Semigroup TT would be uniformly continuous. So we define, so given A, okay. So here, I mean, be careful about this statement. It does not give any particular semigroup. It talks only about generator. Okay, it talks only about A. Okay, it is just saying that, okay, A is in the infinitesimal generator of a uniformly continuous semigroup. Okay, some semigroup. Okay, you have, okay, it is you can identify A as, you know, generator of some uniformly continuous semigroup. Then A is boundary linear operator. Okay, it is saying that. Okay, so that means to prove this type of statement, we have to cook up the semigroup also. Correct. So the most natural way to cook up a semigroup from a generator is taking this e to the power Ta. Why is it so? Because remember that semigroup has this property that that T of T, composition T of S is T of T plus S. Okay, so here product composition, okay, that thing is giving me the T plus S. Okay, so that thing is naturally true for exponential maps. Because here if we have T composition Ts, okay, we can define using the series expansion of exponential map. So that would be e to the power of a could be defined as, you know, limit of I plus a plus half a square plus 1 by 3 factorial, you know, a to the power 3 plus etc etc etc. Okay, so these series convergence, okay, and that converges because if you take the norm, you know, that norm would be converged because this is a boundary operator. So that converges, so the limit I can always define. So this is well defined thing. So using that we can define this semigroup. And for this kind of definition, of course, it satisfies the first property T0 is e to the power of 0, that is identity operator, and second property, that semigroup property, it satisfies that. And then one should also check that this semigroup what we have defined, whether indeed A is the generator of this semigroup. Okay, that also needs a proof. So these are the things what we are going to see step by step. Okay, so for the time being we just define this. So this is a candidate semigroup for which A is actually generator, but we need to show each and every these things. Okay, so we need to show that first A is generator of TT, and second is the TT is uniformly continuous. So if we show these two things, then we are done with this reverse side. Okay, so we start with this. That Tt minus I. So first we prove the second property. Okay, Tt is uniformly continuous. So Tt minus I norm. So I need to show that this norm goes to 0 as small t goes to 0. Okay, so this norm of this difference is equal to limit n tends to infinity. So Tt now I am writing its expression e to the power Ta, but e to the power Ta we understand as limit of that series expansion. So I am writing down the series itself. Okay, n is equal to 0 to capital M Ta to the power n by n factorial. Okay, and here there is a typo, it should be n, not m. N is equal to capital N is equal to goes to infinity, small n is equal to 0 to capital N, this thing minus I. So this thing is just, it is just rewriting these things. Okay, so Ta I am just taking common here because n is, when n is equal to 0 appears in this series, then I am going to get Ta to the power 0, that is identity by 0 factorial. That identity and this identity would cancel each other, correct? And then what I would be left with on n, small n is equal to 1 to capital M, and then there we would always have Ta and Ta whole square, etc., those terms. So I can take Ta common. So I take Ta common from there, and then what remains is Ta to the power of small n divided by n plus 1 factorial. So, I mean, I could have written n here, n minus 1 here, but then I should have written n is equal to 1 to capital N. But I would like to substitute this thing so that I get n plus 1 factorial to the power n, and small n is equal to 0 to capital N. Okay, so this is a nice expression, and then from this norm we get this upper bound. So this norm of this thing is less than or equals to t times norm A, and then the norm is going inside the summation, so it get less than or equals to sign, n small n is equal to 0 to capital N t norm a to the power of n divided by n factorial. Okay, so here instead of n plus 1 factorial, I have written n factorial. Why? Because after all, less than or equals to sign is there. So if I replace n plus 1 factorial by n factorial, so I am replacing this by a smaller number. So, but it is the denominator, so I am actually getting a larger number. Okay, so we write down this thing. Okay, okay, fine. So here I am just using this property that norm of a to the power n is less than or equals to, I mean, nth power of norm of a, and also this property that 1 over n factorial is greater or equals to 1 over n plus 1 factorial. Okay, so now this thing is nothing but exponential series as n tends to infinity, correct? And this we can write down as e to the power of t norm a. So we write e to the t norm a, and then t norm a is here. But this is, if some finite quantity here, and now this thing is a finite quantity, and as t tends to 0, this e to the power 0, so this is bounded quantity, and this part is going to 0. So we are going to get that this is 0. Okay, so hence limit t tends to 0, tt minus I, this norm is equal to 0. So 2 is true. Okay. Now we look at the first property, first condition, that A is generator of TT. So that we need to check here. So we take TT minus identity divided by small t, and we take limit, I mean this quantity, and then here we take the full expression of TT, that is e to the power of these things, and then that we write down in the full form, limit n tends to infinity, this thing. So that we have done in the earlier slide, exactly the same manner. So we get this expression. So now TT minus I divided by t and minus a. So I subtract a from both sides. Okay. So when I do that, so here we see that n is equal to 0 case. N is equal to 0 case, I would have t a to the power of 0, that is identity, and here just in 1 factorial. So I get just identity here. I had this thing. There is some typo here, tt minus I by t, tt minus I by t. So that is this quantity without small t, because small t would be there, and this a times n is equal to 0 to capital N t a to the power n by n plus 1 factorial. Yeah, t a to the power n plus 1 factorial, but something is missing, a is missing. Okay, so there is a typo here that I should get a here. So tt minus I divided by t is equal to limit n tends to infinity a times this summation. Okay, so now I subtract both sides by a. So left hand side becomes tt minus I divided by t minus a here, and right hand side I will get minus a another, and here I have a, here I have minus a. I take a common, so a times limit n tends to infinity, n is equal to 0 to capital N t a to the n by n plus 1 factorial minus I. Okay. Now we take norm both sides, and here norm of product is less than or equals to product of the norms. So here we get norm of a here and norm of this thing. And this thing is what? This thing is already, this thing is actually tt as n tends to infinity. So it is tt minus I, and norm of a is here. However, we have already seen that tt is uniformly continuous. So at small t tends to 0, this norm goes to 0. So this right hand side goes to 0. So that means the left hand side also goes to 0 as t tends to 0. So what does it mean? That means that, okay, this limit converges to a. Okay. So, or in other words, we have proved that this A is indeed the generator of the semigroup. Okay. So Tt minus I, so left hand side goes to 0 as T tends to 0. Okay. So this A is indeed the generator of the semigroup Tt. Okay, so this part is done, and the reverse side, as I told, that okay, showing that A is having norm is finite. Okay, thank you very much.